Welcome, everybody. Thank you so much for being here and attending the seminar. Today, we are very fortunate to have with us Professor Rose Yu. Professor Rose is an assistant professor at the University of California, San Diego, the Department of Computer Science and Engineering. Before this, Rose was a postdoctoral fellow at the California Institute of Technology. Her research focuses on advancing machine learning techniques for large-scale spatiotemporal data analysis with applications to sustainability, health, and physical sciences. A particular emphasis of her research is on physics-guided AI, which aims to integrate first principles with data-driven models. Rose has won faculty research awards from Google, Amazon, and Adobe, several Best Paper Awards, a Best Dissertation Award from USC, and has also been nominated as one of the MIT Rising Stars in EECS. On behalf of everybody here at Penn State, thank you so much for being here, Rose, and we really look forward to hearing about your research.
Thank you, Amuya, for inviting me to give a talk. So as was mentioned, my name is Rose, and I direct the Spatiotemporal Machine Learning Lab, and this is the logo of my lab. And you can see a S&T in the logo of Rose. So let me give you a few examples of what I mean by spatiotemporal dynamics. Perhaps one of the most pressing issues nowadays is the pandemic. And that's also the reason I couldn't fly to Penn State and meet you guys in person. And in pandemic, we wanted to forecast the number of deaths, hospitalization, and cases so that we can inform health public experts about decisions in the coming weeks. So traditional epidemic models based on stochastic simulation, they often require very strong assumptions of disease transmission, of contact dynamics. And on top of that, there are a lot of observed variables, which make it difficult to use mechanistic models for pandemic, for disease modeling alone. So these days, we have a lot of observation data from different counties. And in total, it's about 1.5 million data. So the question is, can we utilize this data combined with traditional dynamics models for disease to make better forecasts? That's one of the examples. So I did a lot of my study in California, right? Both PhD, that's where I overlapped with Amuya and my postdoc. So in the city of LA, traffic is a big problem. So in transportation engineering, again, traditional methods rely on very strong assumptions about driver behavior, but they often do not take account the actual real-world observations. So this video basically shows the traffic patterns from morning to night in LA. And the bubbles represent different accidents happening in different places. So the question again is, can we utilize this observational data, which is recorded at very high frequency, every 30 seconds among several thousands of sensors, right, to better model traffic flows and improve trajectory planning and traffic control? Lastly, right, so there's another global challenge of climate change. So in climate modeling, scientists often rely on very complicated climate models to understand the atmospheric dynamics. So these type of global climate models are often derived from partial differential equations. They're very slow to simulate at that high resolution. So this video shows the temperature variation for the past 50 years across the globe. So nowadays we have a lot of observation data collected by different climate stations. So the similar question is that, can we learn from this data collected by observational stations, and how hopefully can speed up the simulation for climate models? As you can see here, among these examples I listed, from public health to transportation to climate science, and even to many other different fields in science and engineering, the common pattern among these fields is that the data contain very rich space and time information. So this requires us to learn the very rich and complex spatial temporal dynamics in this data, and that's exactly the focus of my research lab. So what makes different from spatial temporal dynamics learning compared with a traditional machine learning application such as images or text data? Well, if you think about space-time data, the first challenge is that we need to model the long-range dependency. So this is an example of El Nino, which is basically caused by variations in ocean temperature across the entire Pacific. So in order to predict the effect of El Nino, we need to model the long-range dependency across space and time. So this is one of the unique challenges of spatial temporal dynamics learning. Another challenge is non-Euclidean geometry. So if you think about traffic sensors, right, they're not distributed on a regular grid like the case of pixels on the image, but instead they're distributed on this very complicated highway roads. And the distance between two sensors cannot be simply measured by Euclidean distance. That's what I mean by non-Euclidean geometry. Perhaps another canonical challenge of spatial temporal dynamics learning is nonlinear dynamics. This means that the underlying system cannot be simply described by a linear model. So a hurricane is a canonical example of nonlinear dynamics. So we also know from mathematical theory that the nonlinear dynamics are sensitive to initial conditions and difficult to predict for a long term. Another challenge that is associated with spatial temporal dynamics learning is multi-scale structure. Because compared with discrete data, such as text data, right, space-time data is continuous, both in space and time. So when we represent them in computers, we have to decide how to discretize them at a different resolution. This will lead to multi-scale structure, and that will cause difficulty in modeling for machine learning perspective. So according to these challenges, we need to have a framework that can address them. The framework that our lab has been building in the past few years is called physics-guided AI. So physics, if you think about it, is a discipline that has been studied for decades about the phenomenon in space and time. So it's a very classic discipline that studies space-time data using first principle method and derived model-based approaches to describe space-time patterns. So in physics, we have tensor networks, that's what I did my PhD on, differential equations that describe the dynamical system, and the symmetries, which is essentially the fundamental laws behind physics. So physics-based models are they can encode domain knowledge, therefore they're sample efficient. So they can learn quickly with a few data points. But physics-based models sometimes can be very rigid because of very strong modeling assumptions. And they can also be computationally expensive due to numerical procedures. On the other hand, in machine learning, we often take a statistical inference approach and derive data-driven methods. So because we're learning from real-world data, our models are more flexible and closer to the real-world phenomenon. So in machine learning, we also have our own tools, such as graphical models, neural networks or deep learning, and variational Bayesian type of models. So machine learning models are computationally efficient, but sample inefficient, meaning that they require a lot of data to train. Sometimes this is not feasible in real-world scientific applications because collecting label data is very expensive. Sometimes people also think machine learning models as black box models because they don't really have the right interpretation for us to understand the phenomenon that we want to model. More importantly, I also want to argue that machine learning models cannot guarantee the physical consistency of their predictions. So for some of the applications that I will describe later, I will show you that these type of errors made by machine learning model will have severe consequences in the context of scientific applications. So as you can see here, these two areas of modeling spatial temporal data have complementary strengths. So it's a very natural idea to combine them together And that's the framework of physics-guided AI. So essentially, we want to use our domain knowledge from physical modeling as inductive bias to help learning, and we can improve the generalization by building in this type of inductive biases, and hence we can reduce the sample complexity of learning, and most importantly, because we are building in physical constraints into the machine learning model, we can ensure the predictions of our model are physically meaningful, and therefore we can increase our trust in artificial intelligence. So in today's talk, I will talk about three different frameworks or general methods that we have built to integrate physical principles with artificial intelligence, with the hope that we can build trustworthy machine learning methods with real-world impact. Any questions from the audience? Let me just pause for a few seconds.
Anybody has any questions at this point?
Okay.
Okay.
So the first type of methods that we developed is what I call the trainable operator. So in our case, right, we are given basically time series, right? It can also be spatial temporal data from time 1 to time t, that's x1 to xt. And if there's spatial temporal, that means that we might also have high dimensional vectors at each timestamp where the dimension corresponding to different locations, right, if we discretize them, or we might have some graph information that tells us the geometric structure of the space that we're trying to model. So our goal basically is to learn a neural network that can approximate the underlying dynamics. And the idea here is we can actually parameterize some of the mathematical operators with deep neural networks. Right? Let me give you a simple example. Let's say we want to learn a function that gives us the map from time t of input xt to y of t, which is the output of this model, right? For now, we can just make it abstractive and make it abstract and not attach it with a specific application. So mathematical operators are common in computation. A very canonical example is the Laplacian operator, right? So this is also used in image filtering, in signal processing, and essentially it computes the filtering, the convolution between this operator f of t with e to the power of negative xt, right? So Laplacian operator is also very useful in graph spectral algorithms when we discretize them. So traditionally, f of t, people need to design them and trying to figure out how to parameterize this operator. But our idea here is, well, since f of t is just a function, we can parameterize them with neural networks. And that's what we call trainable operator. So give you a concrete example of this approach. Let's look at the problem of traffic forecasting. Right, so this is a work published at ICLR, a top deep learning conference. So in this picture, what you're seeing is the speed of different sensors on the road network over time, right? Time in hour. So there are three time series that we're visualizing here in color coded in red, blue, and yellow. These also corresponding to the three different sensors on the top. And we can see here, even though all the three sensors are very close to each other, the time series that are associated with these three sensors are very different. So road 1 and road 2 in blue and red, they have similar patterns, which is the average speed over time. However, road 3, which is in yellow, has very different patterns, just because this sensor is on the opposite side of this highway. So this gives us a hint that perhaps we need a slightly different notion of distance for modeling the spatial correlations among these sensors. And that's exactly the idea of non-Euclidean geometry that I mentioned before. So this is a work done in collaboration with Yaguang at Google and my advisors at USC. So we wanted to model this type of non-Euclidean geometry, right? And which is a type of spatial patterns.
Quick question, Rose. So in the previous example, what would the operator be that you're trying to learn?
Yeah, I'm going to get to that
okay,
soon.
Okay.
You're getting ahead of me, but that's great. And so in spatial pattern modeling, right, we know, let's say if we have an image and we can model the spatial patterns among pixels using a convolutional neural network, and that's shown here. So we can treat the pixels on the image as this type of spatial arranged data points. For traffic patterns, it's slightly different, right? So we're looking at different sensors on this map, and obviously the sensors are not arranged in the type of regular grid showing here, but instead it's more like a graph, right? So the nodes of the sensors on this road network will correspond to the nodes on the graph, and then the edges, on this graph, you can interpret them as the spatial adjacency or spatial proximity between two sensors, right? So that's the graph representation of the road network. So mathematically, we can design the adjacency matrix to represent this graph, right? Because this is it's a directed graph, and then the adjacency matrix doesn't have to be symmetric. So we define this adjacency matrix as follows, where we say that every edge, right, the distance between sensor I and sensor J is proportional to the negative of the road network distance between two sensors. So this is saying that if I look at the travel time between sensor VI and sensor VJ, if it takes longer to travel between these two sensors, then I think these two sensors are kind of far apart. If it takes a shorter time to travel between these two sensors, then I think they are actually quite close to each other in terms of road network. Right, so this is the definition, and with the adjacency matrix, we can define the in-degree and out-degree matrix, which is the row sum and the column sum of this adjacency matrix. Right, you guys still with me? Okay. Then the operator that we want to learn is called diffusion operator. Right, so diffusion operator actually comes from physics, because when we try to model in the diffusion process of a liquid on a surface, and we often use this something called Laplacian operator, which is model the second order derivative of the fluid density. But that's on the continuous space, right? For graphs, that's slightly different. Actually, for a graph, if you visualize it, right, we have some traffic density centered in this red node, and the diffusion process is saying that this traffic density flow would start to diffuse to the first neighbors and then to the second neighbors and so on and so forth. So we need to discretize basically the diffusion operator on the graph, actually that corresponding to the phenomenon stated by this theorem. So this is from Tan et al. 2016, which established the diffusion process with the operator called the random walk operator here. So essentially, the statement is saying that if we look at this diffusion process on the graph, right, and then when the diffusion process converges, this distribution can be written as an infinite summation of some coefficients multiplied by a random walk matrix raised to k's power. And the k's power represents the diffusion to the k step, right, showing on the top. And then this operator is essentially the inverse of the out-degree matrix times the adjacency matrix. And you can see here that this operator itself has this parameter theta, which characterizes the speed of diffusion at every time step, right? And our idea basically is to replace these type of parameters with trainable weights in the neural network, and that's actually the key idea behind this paper. So we can define this operator called graph convolution, which generalizes the convolutional operator from Euclidean space to non-Euclidean graphs. And essentially, these parameters theta in and theta out represent the in degree and out degree diffusion. And these are trainable weights in the neural network. And then xt represent the input at time t. So you can think of them as the concatenation of velocities across all the sensors at time t. So xt is a vector, right? And the shape is basically the number of sensors multiplied times the number of features. So the features can be the velocity, the volume, and something else. So what this operator does essentially is try to transform this input to some latent representation according to the graph geometry, right? So if we do not have this graph geometry, then this will be a linear operator that transforms according to theta, right? But because of this inclusion of the graph geometry, we can account for the spatial dependencies in the graph, right? So we can basically plug in this operator into any existing deep learning architecture that we are familiar with to capture the spatial dependency, right? And that leads to our model, which we call diffusion convolution recurrent neural network. And that's basically combining diffusion convolution, which I mentioned before, with our familiar recurrent neural network, right? So in forecasting, we have a sequence of graphs, right? So these represent the snapshots of traffic flow across time. And our goal is to forecast into future, right, which generate a sequence of graphs again. And note that here the graphs are fixed, right? So that represent the sensor network. They never change. And the features on the nodes are changing over time and represent the graph signal. And this model takes the sequence of graphs, transforming them into latent representation using an encoder, and then using the encoded information to make predictions through this decoder. But both an encoder and decoder, they are using the diffusion convolutional recurrent neural network layer. So what is this layer? Well, if you're familiar with recurrent neural network, right, essentially given the state of the system, xt, it tries to map the state into some hidden state using this nonlinear function, f, right? So this hidden state, is recurrent because you can see that hidden state is updated from time t-1 to time t, right? And output is going to be some nonlinear function again on this hidden states. So as you can see here, the operator between this weight matrix and input is matrix multiplication, right? So in order to capture the spatial dependency, we can simply replace the operator of matrix multiplication with our own defined graph convolution. And that's basically shown here. So we can simply replace the matrix multiplication with the graph convolution to account for spatial dependency, and that will become our defined diffusion convolutional recurrent neural network. And obviously, you can think of many extensions of this work, but plug in this operator into other type of neural network architecture, right? Say the convolutional LSTMs, the transformers, and other things that you can think of. So let's look at the prediction performance. I also want to note that this model was actually deployed for forecasting road network traffic in Google Maps, and then also deployed for a ride-sharing company to forecast their traffic demand services. So this is an experiment on a very small scale for academic research purposes, but I want to note that this model has been scaled and deployed in real-world large systems. If we look at the comparison for LA and San Francisco, that Bay Area, right? So we're trying to forecast 1 hour ahead traffic. So the sensor data is at the frequency of every 5 minutes. So we're trying to forecast 1 hour ahead, given the history. And we compare with a bunch of models, right? Historical average, ARIMA, vector autoregressive models, support vector regressions. These are classic time series models. Fully connected layer, LSTMs, right? These are time series deep learning models, but they don't model the spatial dependency. In contrast, our model explicitly model the spatial dependency with the graph convolution or diffusion convolution. So you can see that in terms of mean absolute error, ours is the lowest across 2 data sets, and the error is about 3.3 miles per hour, right? So the average speed in LA is about 70 miles per hour, and this model is able to forecast 1 hour ahead with 3.5 miles per hour error. We look at the predictions, we can see that the model has learned the center of diffusion, right? So Amuya might be very familiar with this map. So this area represents, the Beverly Hill area, and this is the downtown area close to USC, right? And then this area is essentially the road to Disneyland. So these are the diffusion centers identified by this model as basically the most congested area in this map. And we can also look at the forecasting performances of this model compared with LSTMs. And you can see that This is the mile per hour versus different 24-hour rollouts, right? Compared with the baseline model, which is in orange, right? Orange is our model. The green is the baseline, right? Then the blue line is the ground truth. So we can see that the reason our model can do better than LSTMs is that we can capture this type of dip in the traffic flow much better than the baseline models. Right, that's one example. And you can get the high level idea, which is to parameterize the mathematical operators with trainable weights. Right, so with that example, we also extended this method to another more challenging problem of forecasting turbulence flows. This work was published at KDD, one of the largest data science conference. So turbulence essentially models the evolution of very complicated fluid dynamics. Right? So this video shows two types of fluids, cold in blue and warm in red, interacting with each other, and this creates very intricate patterns of turbulence. And this turbulence is called Rayleigh-Bernard convection. It resembles the dynamics of Nino when the south, a warm fluid in the south interact with a cold fluid in the north, and that creates the dynamics of Nino. So simulating this type of fluid is extremely time consuming. So this video alone, even though it only played for 3 seconds, it took several months to simulate. So our goal here is to develop surrogate models that can make similar predictions but speed up the simulation significantly. And this is a collaboration with my PhD student and our collaborators at Lawrence Berkeley National Lab. So again, we took inspirations from the classic computational fluid dynamics community. Right? We know that turbulence are governed by Navier-Stokes equations, which describe the motion of viscous fluids. And in CFD, there are classic techniques such as Reynolds averaging, which is saying that given the velocity field W over space x and time t, so you can think of it as a video. So this video evolves over space x and time t. Reynolds averaging separates this velocity field into 2 parts. The first part is some averaged velocity field over time, right? And then the rest is the residual. So this is an approximate technique to calculate the turbulence, which is doing spatial averaging. And likewise, you can extend this method to do spatial averaging, right? Which is large eddy simulation. So large eddy simulation also separates the velocity field into 2 components, and one of the components is temporal averaging. So this type of ideas are very widely used in the CFD community. It resembles a multi-scale behavior of turbulence. So this is a plot that's very well known in the turbulence community called Kolmogorov scale plot. It represents the turbulence energy cascade over scales of turbulence, right? So if we look from this direction, then the high energy represents big turbulence eddies, big vortices. And if you look at this end, it represents the energy of small vortex, right? So this type of cascade plot, which characterizes the turbulence energy cascade over the scale. So our idea is essentially replacing the filter operators, which is a convolutional operator, right, in Ranson-Auier coupling with trainable weights. Right? The spatial filter can be replaced by a convolutional neural network. The temporal filter can also be replaced by a temporal convolutional neural network. And to do that, we designed our model called Turbulent-Flow Net. Right? Essentially, we have the velocity field. We pass into a convolutional neural network that will give us the spatially filtered components. We do the same, feed the velocity field into the temporal filter that give us the temporal component, and we model the residual with another network. For each of the network, we use a UNet, which is a multi-layer residual convolutional neural network. So each component represents a separate encoder with a shared decoder, right? So this is also trying to capture the multi-scale behavior in the turbulence. If you look at the predictions, right, our goal is to forecast the turbulence evolution while significantly speed up the computation. So this is the average time per frame simulation, right? The most important result is here, where you can see our model TFNet only requires half the time of the numerical method, the lattice Boltzmann method, used to simulate this turbulence. And this represents a significant improvement of using deep learning methods to speed up turbulence simulation. But most importantly, that we need to guarantee that this prediction of turbulence are physically meaningful. So if we look at the other baselines, such as GANs, ResNet, or convolutional LLTMs, these type of deep learning models are designed for video prediction, and they're not specifically tailored for forecasting this type of physical dynamics, right? So because our model is inspired upon techniques from CFD, so this hybrid approaches guarantees the physical consistency of our predictions, and that's shown on this plot. Right, so this is the energy cascade plot I mentioned earlier, right? This shows the multi-scale energy cascade over wave number, which is, you can understand wave number at the size of the turbulence, right? So the solid line is the ground truth. That's from the simulation. And then the two dashed lines represent a theoretically predicted Kolmogorov scale. Right? The closer to the solid line, the better, right? You can see that two variations of methods, TFNet and the constrained TFNet, have the closest energy cascade behavior to the ground truth, whereas UNet or ResNet, they have very different type of behavior. This is because they do not capture the physical behavior of the turbulence, so they cannot generate physically meaningful predictions. So if you look at the actual predictions, right, this is on the 2D turbulence, which is, you can understand that as pouring milk into coffee, and when you look at the little eddies on the surface of the coffee, and that represents the two-dimensional turbulence. So what you expect to see is two types of fluids interacting with each other in the circular pattern, and you're looking at it from a bird's view, right? That's your expectation. And let me play the video for you, right? So the target is this type of vortex that interacting with each other in the two-dimensional plane, and our model can capture this behavior quite well with even small scale dynamics. In contrast, the ResNet or GANs, they only predicted the very smooth behavior, and they lost a lot of the detailed small scale dynamics. Right, that's the first framework. And the second framework that I want to talk about is actually quite intuitive, and this is residual learning. Residual learning is saying that we're still given some time series, and we want to learn the underlying dynamics model, right? And this dynamics model gives us a forecast. So let's say we have the input from the history x0 to xt. We want to forecast the future from xt plus 1 to xt plus h, right? H is now forecasting horizon. So the idea behind residual net learning is saying that we can decompose this model into two parts. One is with the physics-based model, we call it G, right? And we know that physics-based models are not perfect, right? They have assumptions, they have numerical simulation difficulties, and also have unobserved data that cannot predict. And therefore, we attach this part with a learned model, and that's a machine learning model, right? So combined together, it represents a better model. So this is a very simple idea of residual learning. But actually, this simple idea works quite well in practice. And actually, we use this to model the COVID-19 forecast for CDC. So we're also part of the official team to forecast the CDC, to participate the CDC forecasting challenge to forecast the weekly deaths. This is a screenshot I took yesterday for the COVID-19 forecasting, and our team is here, right? UCSD and EU, and we forecast weekly deaths and send updates every week. So this is a work in collaboration with my students, our collaborators at UCSD and Northeastern. So the physics models we use here is from our collaborator, is called DeepGLEAM, representing Global Epidemic and Mobility Project. So the nice thing about this model is it combines the real world data with spatial human mobility, right? So it models the airport network, the community network, and the population, and use this information together with stochastic simulation. So this model itself is the physics-based model, and it's very accurate. They actually even won the challenge for Ebola forecasting several years ago. So There's some difficulty of using the GLEAM model alone because it doesn't cannot account for the partial observations, and even the data itself has some error due to reporting. So our idea here is to simply learn the correction term of GLEAM. So we have the observational data, right, from CDC or Johns Hopkins University, and we basically subtract the predictions from the GLEAM with the real world data, and that gives us the correction term in the data. And we basically use the diffusion convolutional neural network that I mentioned before for traffic forecasting and adapted slightly for forecasting COVID-19. So we have the travel graph. Right now we don't have the road network graph anymore, but instead we have the travel graph. And then we can use the same model to forecast the future progression of disease. And this was on the white paper listed here. So this model turns out to be quite effective. So we looked at the probabilistic forecast of this model with two types of probabilistic forecasting methods. So I will not go into details of how we make it probabilistic because the model I mentioned of diffusion convolution is deterministic. Essentially, we use quantized regression and stochastic gradient MCMC to make the prediction probabilistic. It generates confidence intervals for different states. But the most important result is that we need to compare the deep learning model with this hybrid model, right? Because COVID-19 is actually a very small data set. So we only have weekly data about number of deaths or hospitalization from different states, right? So the data is very sparse. If we just use the deep learning model alone, the error is huge. That's in green bar. So if we use the GLEAM model, which is a physics-based model, it gets us somewhere, but not as good as the hybrid model with DeepGLEAM, which learns the correction term of the residual, right, the COVID-19 residual. And here is the visualization of the actual prediction. We can see that the reason deep learning model doesn't do well is that in this line, it only captures the mean behavior of the COVID-19 progression, but it doesn't capture the small scale, like very zigzag behavior in the dynamics. And that's learning the residual. And you might think of this idea quite simple, but let me show you another example of how powerful this idea can be in forecasting, the turbulence flow for controlling the drones. Right, so this is a work done with my collaborators at Caltech. Essentially, and this published at ICRA, a top robotics conference. So essentially, we're looking at this phenomenon of something called ground effect, which means when we fly a drone closer to the ground, because there's air turbulence that's being generated by this drone, and the air turbulence will cause the drone to tumble, sometimes even to crash. So this is a big problem in the aerospace engineering community because we cannot characterize the behavior of air turbulence. So our idea is a hybrid model, right? So we have some physics-based model that describes the motion of the drone, right? We have the position, velocity, and angular velocity, etc. And these are described by the set of differential equations. So you can temporarily ignore these differential equations, but just only pay attention to the color of the variables. So you can see that everything in black, we actually already know in physics, or we can calculate them or measure them directly. But the variables in red, these are caused by air turbulence. So we cannot estimate them correctly, and we cannot even calculate them correctly because of turbulence, right? So we're learning the residual term here with the deep neural network in order to predict the next state of this drone, right? And this idea, again, is to learn the correction term, the residual learning, to approximate the residual with the deep neural network. But it's turned out that simply approximating a deep neural network for this term is not enough. So we almost crashed the drone with this simple idea of residual learning. It turns out that, in modeling this type of dynamics, deep neural network actually can be too flexible. So in order to address this problem, we added another correction to this deep learning model, which is to regularize the behavior of deep learning with spectral normalization. So the spectral normalization idea is, in order to constrain the output of this functional approximator, we need to constrain the Lipschitz constant of this deep neural network in order to make sure the learned dynamics are stable. And that's critical for the drone control experiments. And the way you can implement this is essentially normalize the weights during training by the largest singular value of the weight matrix. And this technique is not new. In this context, it has been studied well enough in GAN training and other type of deep learning, generative training. So this is residual learning, right? Let me show you the video. So essentially, we're trying to ask the drone to track flying around the table. The top one is our model, and the bottom one is the baseline. And you can see that because our model can learn the air turbulence effect, then this drone is able to fly around the table very closely without crashing. And the baseline model, which is a popular method used in control community, has to fly very far away from the table to be safe, because it doesn't know about the effect of air turbulence. So this is particularly useful in the case of disaster rescue, where we want to fly a drone into a tunnel to take videos. Right, let me show you the effect of spectral normalization, which is the key idea of this work. So we are using residual learning to use essentially using a deep neural network to learn the correction. But simply using learning correction is not sufficient for stable dynamics. So we regularize this correction with spectral normalization. And this is shown here, which essentially highlights the effect of spectral normalization. So in summary, spectral normalization helps our model to learn better dynamics, and it generalizes better to new domains. So if we use spectral normalization, right, then we can see that this linear trend between vertical distance and vertical velocity extends into the new domain, whereas without spectral normalization, this trend will disappear in the new domain. And this is even more obvious in the flying a table experiments. We can see that with spectral normalization, the model is able to learn the shape of table from a few samples, whereas without spectral normalization and using a simple residual learning, the model will not be able to learn the shape of the table and therefore fly correctly. So that's the second framework. Right? Let's stop for a few seconds and wait for some questions.
So Rose, one question, how are you getting the ground truth for these residuals before training? I mean, how do you know what are these residuals actually supposed to be when you're training the network?
Oh, so in this case, we actually don't need the residual for the ground truth, right? Because once we learn the residual, then we can generate the next state and we can measure the next state, which is the position and velocity of the drone.
Okay. And how do we know that that next state is a desirable state or it's not a desirable state?
Oh, we know that because we can measure them.
So you have some desired trajectory, you have some prefixed way
That's
in which
yeah,
you want the
exactly.
you want
It's
the
a
drone
tracking.
to fly.
That's right.
I see. Okay.
Very good question. Okay.
And
Then the last.
I would assume that this would a more fun test case would be that you have a fan that's that's blowing air in front of a drone and testing with that. So
Exactly. That's actually what we were trying to do, right? To test the facility test the drone experiment in the turbulence fan tunnel. We have a wind tunnel, right? Actually, and we can test the drone in the wind tunnel. That's something that we have been trying to do.
I see.
Okay, then the last one that I want to just briefly mention, so we're actually running out of time. So this is some new things that we did to combine physics with AI, right? This is the third framework, which we call Equivariant Learning. So in the past two things, we talked about learning the mathematical operator or learning the correction term. Let's assume that we already know something about the physics model that governs the dynamics. But in some cases, we don't even know the physics model of the underlying data we want to model. We only know some high-level conservation laws of the phenomenon. So how shall we pursue in that case? Right? And equivariant learning is exactly trying to solve this type of issue. So it draws inspiration from this theorem called Noether's theorem, which connects the symmetry with the conservation laws. So Noether's theorem saying that for every symmetry, there's a conservation law. For example, the conservation of momentum corresponding to the time-space translation symmetry, right? So the idea of learning equivariant learning is to learn a function f that is G equivariant with respect to some groups. So essentially, if we apply a group transformation on the input, then we want to learn a function f that can automatically recognize this transformation in the input and then apply that to the output of this function. So you see that equivariance essentially means that we can switch the order between the function f and the group transformation. So that means if an input is transformed by a group, then the output is also transformed by a group, right? That's a high-level idea behind equivariant learning. So in the forecasting case, we're actually using a neural network to approximate the underlying dynamical system. And instead of transformations, you can think of them as, corresponding to laws of physics in energy conservation, momentum conservation, etc. So this is the work that we did in iClear this year, is essentially built-in symmetries into deep learning for generalization. Now, this is done by my PhD student and postdoc. So before we touch upon this framework, then I want to just briefly recap on some basic knowledge and group theory. Right, so in group theory, we know a group is just a set. Right, the group has a composition map that takes two elements of the group and map to itself. So identity is in this group, in the set, right? And for every element in the set, it has an inverse operation, right? Concretely, we can think of rotation. The 2D rotation, or SO2, is a group, right? Because non-rotating or identity is in the group. And if we rotate 45 degrees to the left, we can always rotate it back, but with another 45 degrees. And therefore, for every element in this group, it has an inverse operation. So for every group, we can define a representation, which is essentially the matrix representation of this group transformation. It has to satisfy group homomorphism, meaning that if we apply this matrix to two elements of group, we can decompose them into row of G1 and row of G2. So this matrix have to be invertible, right? Because the group element need to be invertible. And it's a linear map, right? So we can represent them by matrices. So one important thing to know is that even for the same group, we can have different representations. Let's say if we're looking at the cyclic group of order 4, we can either represent them with a 2x2 matrix, which is a rotation matrix. So this is trying to transform this square by 45 degrees, or by 90 degrees. By 90 degrees, we're rotating this red dot by 90 degrees, and we can represent this representation by a rotation matrix. It's 2x2. Alternatively, we can think of in the following way, where we can represent this group by a permutation group of order 4. So this is a 4x4 matrix, and this is trying to permute the vertex on the rectangular in the way that is similar to the final result of this left operation. So this is saying that even with the same group, we can have different matrix representations to represent this group transformation. So the idea of equivariant neural network, which is a very recent type of literature in machine learning, is to learn a neural network F that's actually equivariant with respect to this kind of transformation. So in order to do that, we need to define the intermediate matrix representations for this function, right? So we have a fully connected neural network, for example, then the input representation and output representation of the fixed because the input and output features are defined already. But the things we can do to make this neural network equivariant is that we can change the intermediate representations to the type of representation that will preserve equivariance. So there's a key result from Weiler and Sesa, which give us a guideline of how to design convolutional neural networks that are group equivariant. So it shows that as long as the kernel satisfies this condition, which means there is a input representation transformation right multiplied to the kernel, and then there's the inverse of this group transformation left multiplied to the kernel. If it can be decomposed in this way, then this convolutional layer is always group equivariant. So the question now is, how do we actually come up with this type of representations for different groups? And that's what our contribution here for this paper. So we looked at the turbulence forecasting case, right? And I think because of the time limitation, I will not go into details of how we actually calculate the representation matrices for each groups. But the high level, the benefit of this is that in a lot of times, machine learning models cannot generalize. So if we change the testing data in some new domain, let's say we rotate it or we scale it, and in distributional wise, they look very different from the training data. So in that case, machine learning models will fail miserably, especially deep learning models. But the nice thing of equivariant models is that even though the data of distribution have changed, the law of physics does not change. And because of that, the model can recognize these changes in the test distribution and being able to adapt and react to these kind of changes. And so if we look at the turbulence forecasting example, right, if we rotate the distribution by some degree, right, then the non-equivariant model will completely fail in this case, or equivariant model will be able to recognize this change in the test data distribution. Similarly, we can apply that to uniform motion and scaling. So this is a real-world experiment on the ocean current forecasting data set. And similarly, we will keep the training data fixed, but changing the testing data. So the way we change the test data is to upscale the test data by different factors. And intuitively, non-equivariant models such as ResNet will not be able to adapt to this kind of change in test distribution. So the error explodes really quickly for ResNet, whereas the equivariant ResNet, because it can recognize this group transformation and is inherently equivariant, it stays robust against this type of changes in the scaling. To conclude, I talked about the 3 types of lines of work that we have done in order to incorporate principal physical laws into deep learning model for learning spatial temporal dynamics. I talked about trainable operators, which is to replace mathematical operators with trainable weights, with the hope that we can provide more flexibility in the learned model and reduce manual efforts. We talked about residual learning, which is to learn the correction terms or the residual terms of the imperfect physical models. This is trying to resolve the case where we have limited samples, where we cannot just use the data-driven model such as deep learning to learn alone. Equivariant learning is to incorporate physical laws of symmetry to guarantee that the predictions can follow the laws of conservation. In terms of future work, actually, we're very interested in quantifying the uncertainty of the predictions to generate probabilistic forecasts. And I know that Amuya also works on multi-agent interactions. So that's something we're also exploring to understand the complex multi-agent behavior in this kind of dynamics. So if you want to check out the code and the data, it's all available on my website. You can also follow me on Twitter. And I want to thank the funding agencies for supporting this work. Thank you.
Thank you so much, Rose, for that wonderful talk. I guess we have about 5 minutes for questions. Does anybody have any questions? Mariam, Hangzi, anybody?
Yeah, I have some more quick questions. So I think that you mentioned about the equivalent learning in that network, and you show a theorem in the PowerPoint, but I think the network, you show is upsampling. So first the dimension is low, and then higher and higher, and then getting low. So I was wondering, is there something, is there some theorem or something behind that design, or maybe perhaps you can share the PowerPoint.
Oh, sure.
Yeah. I think before that. Before, yeah, this network. So I was thinking, is there, so why is the network, seems like, upsampling and downsampling? So why the dimension of the network goes up and down? Is there some particular choice?
Oh, this network is just a cartoon. It actually doesn't
represent
the network that we use in the paper. I just meant like, because we can think of a neural network as a composition of functions, right? So you can think of different layers, and they don't have to be the same size. The key part is to come up with the right group representation, row 1, and row 2, to make sure that the entire thing is equivariant.
Okay, I see. Thanks.
Thank you. I guess one question that I had you was about the COVID work, the COVID forecasting work. In that, you mentioned that you were using the same diffusion convolutional neural networks, and you had the travel graph for all of America, which I assume would be quite large. And I would assume that the data that you have is very, very sparse.
Oh, it's not actually that big. So right now we're only modeling the state level forecast. So we have about 50 states, right? So graph is about 50 by 50. So that's not very big.
I see. Okay.
Okay. But you're right in the sense, right now we're looking at county level forecasts, right? So that's about 33,000 or so counties, and that is a scalability question. That's right.
I see. I guess another question. I mean, just from so that I understand where this tool of diffusion convolutions can be used. So it can certainly be used. My understanding is that it can be used in situations where you have this if you have traffic, for example, you can, and the distance is a non-Euclidean, therefore you need this graph representation. And if you have this graph representation and things are diffusing over this graph, you can learn. Replace that diffusion operator with trainable weights. As I was mentioning, we're trying to solve this problem with locust movement. So we have point observations of locust being observed at point A and then point B. And I don't think that there is any issue of non-Euclidean geometry there, because locusts can fly in a straight line from point A to point B, unless they're impeded by some mountain or something else. I guess for them to move in a particular direction, the wind speed also needs to align. But I wonder if, yeah, so most probably, we can assume that it has Euclidean geometry, but it is definitely the case that there is some amount of diffusion that's going on. So if you have a huge locust swarm at location A, that they are going to diffuse to different locations in the next couple of days. But the graph in the situation is not known per se.
I think that's fine, right? I mean, can you still use the diffusion operator, but designing a slightly different graph, right? So the graph doesn't have to be, the actual, actual space on the Earth, right? It can represent, the agents that you're trying to model and how they actually correlate to each other. So the graph, it can be a more general sense of modeling the correlations among different agents.
I see. Okay. Yeah, I'll try reading a paper to see if I have any questions. I'll get back to you. I guess one final question, and this is also something that we've been struggling in our research. And this goes back to the diffusion results that you'd shared. You were showing your prediction performance in terms of mean absolute error, and since that was an actual real world, I mean, it was the predictions there had some real world significance, right? That if you are able to predict better, then you're able to predict traffic better. And yet the evaluation metric that you used was mean absolute error. And you had some difference in at least in the figures that you showed between your model and the previous models that you had, right? And you were doing better by some amount. Now I want to understand, we are facing this tension where we are having to justify to domain experts how much that if we are getting if we are improving the mean absolute error by, let's say, 0.5, how much savings does that correspond to in the real world, right? What does that prediction accuracy improvement of 0.5, what does that translate to in terms of how it's going to be used in some sense? So have you faced this sort of a tension in your research where you've had to justify that, even though this absolute difference might not seem large, that it's not to be viewed in absolute terms, but this difference can translate into this much amount of savings, or this much amount of cost savings, etc.
Yeah, I think that's a very good comment. I think, particularly for the traffic work, like we already know that, the state-of-art methods cannot even forecast in more than 15 minutes. And that was a limitation of all the existing model, not because of my work, because of, my collaborators who have been working on this field for like more than 30 years. They know that the bottleneck is, the forecasting horizon, And once we were able to make forecasts for 1 hour, we basically need very little justification that this model will have an impact. And that's why, you know, as I mentioned, this model was already deployed in production, and the people are using it right from day to day. And I don't think we need more justification for that particular number.
I see. I see. Well,
but in general, I think it is a very good question, right? It's like how much is enough for real world application, because deployment always costs more, and people wouldn't bother to deploy somebody's algorithm. It's just only about 1% of improvement.
right.
Consider the overall cost is a very difficult multi-objective optimization problem, right? So I think we definitely have faced similar issues before, but our strategy is always, we try to identify with domain experts. And as you can see that we do work a lot with domain experts from different area. So we try to work with them closely and identify what really matters, so that we're not, making incremental improvement, but we're really solving an important problem. So, on that end, even 1% improvement is a big improvement.
I see. I see. I see. Okay. I guess we're out of time. So, I don't want to hold you for longer. Thank you so much, you.
No worries.
Thank you so much, Rose, for coming here and giving this talk. We really enjoyed it, and thank you everybody for attending. If you have any other questions, I'm sure Rose won't mind if you email her your questions.
Yeah.
Thank you.
Yeah. Take care. Bye.
Bye-bye.